So what if I told you that like 90% of the reason today's AI is getting so incredibly smart has, well, almost nothing to do with genius coding?
Yeah, it completely upends the narrative we usually tell, right? I mean, we all like to imagine this lone engineer at a whiteboard, writing out some elegant equation that changes the world.
Right, the classic movie trope.
Exactly. But the reality of this current AI arms race is significantly more industrial. And frankly, it's heavily dependent on sheer capital.
Just who can buy the biggest warehouse of computer chips,
Pretty much, yeah.
which is wild. And figuring out that exact balance, between brilliant engineering and raw brute force, it's essentially the defining question for anyone tracking tech right now.
Oh, absolutely.
And we finally have the definitive answer. So welcome to today's deep dive. We are looking at a really comprehensive new study from MIT researchers.
Yeah, Mertens, Fischl-Zoni, and Thompson. Published in February 2026.
Right. And they analyze a massive data set. I'm talking 809 large language models released between October 2022 and March 2025.
Which is basically the entire modern era of AI right there.
It really is. So, okay, let's unpack this.
Sure.
Because if we want to cut through all the marketing hype and actually understand the recipe behind the AI that you use every day, we need to look at what they found. They didn't just rely on like self-reported vibes from these tech companies.
No, not at all. What's fascinating here is they literally tore open the mathematical hood of the industry to see what actually makes these models tick.
And they used a really specific method to do that, right?
Yeah, it's called shapely variance decomposition. It's a way to separate the marketing from the math, essentially.
So Shapley variance, it's basically like trying to figure out who contributed what to a group project.
Yeah, that's actually a perfect way to visualize.
Like you mathematically remove one variable at a time, say the total compute power, and then you see how much the final test score drops. And that isolated drop in performance, that's the exact credit that specific variable gets for the final result.
Right, and to get that final test score, they used what's called the MMLU Pro benchmark. It's this huge test of reasoning across math, law, history, science, you name it.
The gold standard test right now.
Pretty much. And they mapped those scores against the model's training compute, so the raw processing power measured in FLOPs, or floating point operations.
Right. And by tracking those FLOPs, along with release dates and the specific developers, the researchers isolated 4 distinct factors, like 4 ingredients that explain why one AI model is better than another.
Exactly, 4 main ingredients.
Okay, so let's break these down with an analogy, because I was thinking about this, and it feels a lot like motorsport, like Formula One.
Oh, I like that. Okay, lay it out.
All right, so the first factor has to be the pure hardware advantage, the raw FLOPs. In a race car, that's just putting a massive engine in the car.
Right. The researchers classify that as scaling effects. It represents the brute force component, literally just making the model bigger by throwing more training compute at it.
Okay, so that's the engine. But if scale is just raw hardware, there has to be a metric for the foundational science the whole industry uses. In the car analogy, that would be the invention of better tires that any racing team can just go out and buy.
Right, the baseline tools. That brings us to the second factor, which is shared algorithmic progress.
Which means everyone benefits.
Exactly. It captures the industry-wide innovations that lift all boats over time. Things like improvements to the transformer architecture or new open-source discoveries that anyone can implement.
And the paper had a crazy stat on this, right?
Yeah, they found that between late 2022 and early 2025, this shared progress alone was equivalent to a 7.5x increase in compute efficiency.
7.5x. So you'd only need a fraction of the raw processing power to get the exact same performance in 2025 as you did in 2022, just because the basic science got better.
Precisely.
But obviously, not all companies share everything. So the third factor has to measure the proprietary stuff, the specific developer's coding. In our race car, this is the team's secret aerodynamic design.
Right, the proprietary engineering. The researchers actually termed that the company's secret sauce.
Secret sauce. I love that they officially call it that.
It works perfectly, right? It isolates the developer-specific technology. It accounts for how a company structures their data filtering or their proprietary fine-tuning techniques to squeeze more performance out of the exact same amount of compute compared to like a generic baseline developer.
Okay, so we have the engine, the tires, the aerodynamics, but there's still a fourth factor. the residual variation,
Yeah, the model-specific technology.
which I guess would be like the random track day adjustments the pit crew makes right before the race.
Exactly. Because even within the same company, using the exact same secret sauce, two different models might perform very differently.
Just based on quirks in the training run.
Yeah, idiosyncratic quirks, specialized optimizations. It's the wild card.
Okay, so keeping those four ingredients in mind for you listening, the scale, the shared progress, the secret sauce, and the model quirks. Which of those do you think actually matters most when a new world-beating AI drops?
Well, applying that framework to the data reveals something incredibly stark about the industry right now.
Yeah.
When they isolated the data for the absolute frontier of AI, meaning the models hitting the very highest scores, they found that 80 to 90% of the performance differences are driven purely by the size of the engine.
Wait, really? 89% is just scale.
Almost entirely driven by scale, just brute force compute.
I mean, looking at the numbers in the study, the leap is staggering. They tracked Meta's Llama 270B model from July 2023, right?
Right, which scored about 30.2% on the benchmark.
And then you fast forward to OpenAI's GPT 4.5 in January 2025, and the score jumps to 84.6%. But to get that jump, to get to the frontier, they increased their training compute by a factor of nearly 5,000 in about 18 months.
5,000 times more compute. Yes.
That is a blistering pace. I mean, inherently, Moore's law alone isn't saving them here. The microchips aren't getting 5,000 times better in a year and a half.
No, definitely not. They are physically building larger and larger data centers to brute force this evolution. It's a massive capital expenditure.
Wait, so if 90% of the frontier is just throwing more computer chips at the wall, isn't the whole idea of a tech giant secret sauce actually a myth? Like, are they just buying their way to the top?
Well, if we connect this to the bigger picture, it's not a myth, but it means the barrier to entry at the frontier is currently insurmountable for most organizations.
Because you just can't afford the chips.
Exactly. The share of performance explained by scale actually rose over time in their data, moving from 77% to 88%.
Wow.
Yeah, so you simply cannot outcode a 5,000x deficit in raw power at the very top. Maintaining AI dominance right now requires securing vast, ever-expanding physical infrastructure, period.
So if you don't have the hardware, you fall behind. But if the bleeding edge is fundamentally just this billionaire's hardware race, the proprietary engineering, that secret sauce, it has to show its value somewhere else, right?
Oh, it does.
Like, what happens when you restrict the size of the engine? Does the secret sauce actually make a difference?
It becomes the deciding factor. So across the entire data set of all 800 models, the company's secret sauce explains about 14 to 18% of performance differences.
Okay, not huge, but significant.
Right. But when they filtered the data to look specifically at major developers building smaller models, that number jumped up to 33.7%.
Oh, wow. So a third of the performance is just how good the company is at coding.
Yes. When you restrict the brute force, proprietary efficiency completely takes over.
Here's where it gets really interesting, especially for the business side of things. Because we're talking about the AI that runs locally on your phone or gets integrated into, like, enterprise software without racking up massive cloud computing bills.
Exactly. Smaller, practical models.
And the efficiency gaps here between these developers are massive. Like, the study estimates a company like DeepSeek operates with a compute factor of 2.3x compared to generic baseline developers.
Meaning they can hit the same capability using less than half the compute of a startup.
Right. But then the contrast gets even sharper. Microsoft's compute factor is estimated at a staggering 60.5x compared to those same baseline developers.
60.5x. It's a huge advantage.
A 60x efficiency advantage is an almost unassailable financial moat. I mean, to achieve the exact same level of intelligence, a startup would theoretically need 60 times more raw computing power than Microsoft.
Yeah, good luck securing funding for that.
Seriously. And the study notes that all the major developers they tracked, Meta, Google, OpenAI, Anthropic, Quinn, NVIDIA, 01AI, XAI, they all demonstrate this substantially higher baseline efficiency than small developers.
And the mechanism behind that massive gap, it really comes down to deep proprietary knowledge. It's things like how they filter their training data to remove low-quality information, or how they structure the internal architecture of the neural network.
To route information more cleanly.
Right, exactly. A 60x advantage means they've figured out how to make the model learn the core concepts without wasting computational cycles memorizing redundant noise.
Which completely explains how these tech giants plan to survive the inevitable price wars. Because right now, the cost of running an AI, the inference cost, is plummeting.
It's getting cheaper every day.
Right. And if your model requires 60 times less electricity and hardware to give the user the exact same answer, you can offer your service for pennies and still maintain incredible profit margins.
That's the business model, yes. But having that high-level secret sauce doesn't seem to guarantee a hyper-efficient masterpiece every single time.
Oh, right. The wildcard factor.
Yeah, the paper highlights a massive mystery in the data. They found that model effects, that fourth ingredient of idiosyncratic track day variation, accounts for 32 to 47% of the differences in performance.
Nearly half the variance is just random model quirks.
Yeah, across the board. Even when mathematically controlling for the size of the model, the shared science of the era, and the company's proven baseline efficiency. Individual models within the exact same company vary wildly.
That is insane.
It is. Models sitting at the 90th percentile of efficiency translate their compute into performance 41 times more effectively than models at the 10th percentile.
Wait, 41 times? How is that variance so vast within the same company using the same tools? It seems highly counterintuitive that, like, engineers who build a super efficient model on Monday could train a model on Friday that ends up 41 times less efficient.
You'd think it would be standardized by now.
Exactly. How do they not know their own recipe? Why is the actual training of these neural networks still so unpredictable?
Well, it comes down to the underlying mechanics of how large language models actually learn. Training a neural network relies heavily on trial and error. Specifically, a mathematical process called gradient descent, which is trying to find the lowest possible error rate.
Okay.
You're feeding trillions of words into a vast multidimensional matrix. And if the model ingests, say, a massive batch of highly complex coding data before it has fully optimized its basic logic pathways, the mathematical weights might settle into a suboptimal pattern.
Like getting stuck in a rut.
Exactly.
Yeah.
Researchers call it a local minimum. It gets stuck in a mathematical rut. So the exact sequence of the data, slight adjustments to the learning rate, the dark arts of fine-tuning it, is all highly sensitive to initial conditions. It's a chaotic system. It's not a solved science yet.
And the researchers actually point to a high-profile discrepancy in the data that illustrates this chaos perfectly, right? They note that GPT 4.5 performed lower than the statistical model expected it to, given its massive scale and OpenAI's deeply established secret sauce.
Right. It registered a negative model effect in their analysis.
Which is fascinating. And in contrast, Meta's Llama 270B showed a very strong positive internal model effect, heavily outperforming its baseline expectations.
Yeah, and it perfectly humanizes the engineering process, I think. It proves that despite the billions of dollars invested, this is not a deterministic science like building a bridge, where the physics are perfectly solved.
You just follow the blueprint.
Right. There is no perfect blueprint here.
Yeah.
Even the creators don't always know exactly how optimal the internal connections will be until the multi-month training run is actually finished.
Okay, so what does this all mean for you, the listener? Because most of us aren't directly interacting with these 5,000x compute monsters running in private data centers.
No, definitely not.
So if the frontier is dominated by brute force and training is chaotic, how is AI actually benefiting people right now?
Well, the real revolution for the end user is happening just below that frontier. The true impact of technical progress is how it allows developers to compress amazing capabilities into tiny, extremely cheap packages.
Shrinking the models.
Exactly. Looking back at the MMLU Pro benchmark, reaching a 15% score in January 2023 required a massive model. Specifically, Google's Flan UL2.
Which is a model that demanded significant server infrastructure just to operate.
Very heavy, yeah. But fast forward just 18 months to July 2024, NVIDIA's Minitron 4B hit that exact same 15% capability threshold, but it required 50 times less compute to do it.
50 times less compute in 18 months.
And it gets better. When the researchers factored in the broader data set of smaller open source developers, they found instances where hitting the same capability required up to 8,000 times less compute than the original baseline.
Up to 8,000 times. That's unbelievable. I mean, a 50x to 8,000x drop in compute requirements, that changes the entire paradigm of how we use technology.
Oh, absolutely.
We are talking about the democratization of intelligence. The secret sauce isn't just about building some godlike AI that only a multinational corporation can afford to turn on. It's about shrinking existing AI so it runs natively on your phone or in your web browser using almost no battery life.
And doing it without ever sending your data to the cloud, which is huge for privacy.
Right. And the data shows it's even more extreme in specialized domains, doesn't it? Like, they ran this entire analysis on a different test, the Math Level 5 benchmark.
Yeah, which focuses entirely on complex mathematical reasoning, and the divergence there was remarkable. For math capabilities, the shared algorithmic progress represented an 11x jump in efficiency, rather than the 7.5x we saw on the general test.
Wow. And what about the internal model variance, that wild card factor?
The gap between the 90th and 10th percentile models wasn't a 41x difference there. It was a staggering 186x.
186 times more efficient.
Yeah, because developers are aggressively targeting specialized domains, leading to wild efficiency gains in specific use cases.
That's incredible.
It is. But this raises an important question, and it's a dynamic explicitly noted in the MIT paper.
Okay.
While shrinking these models and making them drastically cheaper democratizes access for everyday users and students, it inherently lowers the cost of access for malicious actors, too.
Oh, right. Because the same massive leap in compute efficiency that allows a startup to build like a helpful medical diagnostic tool on a shoestring budget.
Yep.
It also allows a bad actor to run 10,000 highly sophisticated phishing bots from a single laptop.
Exactly. Democratizing the underlying capability simultaneously democratizes the risks. The efficiency curve doesn't differentiate between a helpful application and a harmful one. It just makes both of them incredibly cheap to run.
Wow. Yeah, that adds a serious layer of risk to all this incredible efficiency. So we're essentially looking at a landscape defined by two radically different trajectories right now. On one hand, we're seeing capabilities democratized and efficiency skyrocket for smaller, specialized models. But at the absolute top, the frontier is still dictated by a brute force trajectory that demands a 5,000x increase in compute every 2 years just to stay relevant.
It's a tale of two industries, basically.
It really is. And I want to leave you with a final thought regarding that 5,000x figure. The researchers note that compute grew by a factor of nearly 5,000 for top models in just over 2 years. But the mathematical abstraction of AI progress is exponential, while the physical world we live in has rigid limits.
Very rigid limits.
We're talking about the capacity of national electricity grids, the sheer volume of water required to cool tens of thousands of GPUs running continuously, the reality of spending tens of billions of dollars on single data centers, and the physical bottlenecks in silicon manufacturing.
It takes a lot of raw materials to keep that engine running.
Exactly. So when, not if, but when, that brute force scaling inevitably hits a physical or economic wall, what happens to the AI race? When you can no longer simply buy a warehouse 5,000 times larger than the last one, will the companies harboring the best proprietary secret sauce and the highest engineering efficiency suddenly inherit the frontier?
It's the multi-trillion-dollar question.
Will the competition instantly shift from who has the most capital to who has the sharpest algorithms? Or will the breakneck pace of improvement we've all grown so accustomed to simply grind to a halt for everyone?
Definitely something to mull over.
It really is something to keep in mind the next time a tech giant announces a massive new model. Look past the benchmark scores and ask yourself, is this a leap in fundamental genius or just the next massive withdrawal from a finite physical grid?
Well said.
Thanks for joining us on this deep dive. We'll catch you next time.